Okay, so now let's shift away from the thin film interference. And let's look at first a single slit problem and then a diffraction grating, which is a many slit problem. All right, so we want to know what width of the single slit will produce a first order diffraction minima at angles of plus or minus 23 degrees away from the central maximum with 670 nanometer light. So for single slit diffraction, what happens is light comes in through a single slit and it creates one broad peak, and you have smaller maxima off to the side. And so what it's asking is, where is it that you have an angle of 23 degrees? What slit width do you have to have an angle of 23 degrees between the center peak and the first minima? So what do we know? We know we have our wavelength at 670 nanometers. We know that our theta is 23 degrees, and we've got the first minima, so the first one has an m equals 1. So what's our equation? Our equation is that the slit width, which is often given by A sine theta equals m lambda. Sometimes you'll see it written with a capital D for the slit width. Depends on which textbook you're using. So that's my equation. And what am I trying to find? I'm trying to find A. So A sine theta equals m lambda. I know my theta, I know my m, I know my lambda. So A is equal to m lambda over sine theta. So it's going to be 1 times 670 nanometers. Let's put that into meters now. So 670 times 10 to the minus 9 over the sine of 23. And I get 1.771 times 10 to the minus 6 meters, or 1.7 micrometers. All right, next question. Now I have a diffraction grating. For a diffraction grating, we have, again, an equation that looks very much the same. D sine theta equals m lambda, where D is the spacing between the lines. Theta is the angle of the peak. Again, this is for constructive. M is which order peak it is, and lambda is the wavelength. All right, so I've got a diffraction grating that has 2,200 lines per centimeter. Okay, so every centimeter has 2,200 lines, and so I want to know what's the spacing between them to give me my D. So D is equal to, every centimeter has 2,200. So let me put this into meters. So a centimeter is 10 to the minus 2 meters. So the spacing between the lines is 4.55 times 10 to the minus 6 meters. Okay. Then we're asked, what's the angle between the first order maxima for red light and blue light? So first order maxima, m equals 1. For red light, so lambda red is 680 nanometers, and lambda blue is 410 nanometers. I want to know what's the difference in the angle. So what I need to do is I need to find the angle for each of them and then subtract them. So I want to find, so I know sine theta is equal to m lambda over d, rearranging that equation. So for red, sine theta is equal to m, which is 1, times the wavelength for red, 680 nanometers, 680 times 10 to the minus 9 meters, divided by d, 4.55 times 10 to the minus 6 meters. And so that means that theta is going to be equal to the inverse sine of that. And I get 8.6 degrees. Okay, so I didn't actually have to find what this number is. I could just tell my calculator the inverse sine of that. But if you want to, you can find it. All right, let's do it for blue. So for the blue light, Same thing. So let's call this theta red, and up here, and let's call this one theta blue. So sine theta blue is equal to 1 times, now my wavelength is 410 nanometers, 10 to the minus 9 meters, over d, which is still 4.55 times 10 to the minus 6. So I get theta blue is going to be equal to the inverse sine of that. And so I get 5.17 degrees, let's say 5.2 degrees. All right, so what's the difference in the angle? The difference in the angle is 8.6 degrees minus 5.2 degrees. So I get 3.4 degrees. Okay, so what that means is that when you look through the spectrometer, if you shine white light on it, you're going to see the red light. If I look at a screen, the red light will be here, the blue light will be here. So if this is the center, so the red light is scattered at a bigger angle than the blue light, and so you see a separation of the colors of the light.